Hello everyone. In this video, we'll be looking at analysis of Fourier transform and its application in signal processing. So let's go into the topic. These are the contents that we'll be looking at today. The introduction of what Fourier transform is, and to understand the Fourier transform, look at few properties of Fourier transform that will be helpful in signal processing, and what discrete Fourier transform is. And then we'll be going into knowing about the applications of this Fourier transform in signal processing. Then we'll be concluding the session. So now going into the introduction part. The Fourier transform is a fundamental mathematical tool in signal processing that transforms a time domain signal into a frequency domain representation. We do know that Fourier transform is mainly used to convert the values of the data that we have from one domain to another domain, as you can see over here, mostly from time to frequency domain. The advantage of this is it makes the data studying or the processing of data much more easier. We'll be able to study and analyze the data even more robust and even more efficiently when we do the Fourier transform. This transformation allows engineers and scientists to analyze the frequency content of the signals, enabling applications across various fields, such as telecommunication, audio processing, image processing, and control systems. So now to know what this Fourier transform is in even more deeper way. So the Fourier transform decomposes a signal into its constituent sinusoidal components, providing a frequency domain perspective for a continuous time signal x of t. Let's take a time signal x of t, and to see the Fourier transform x of f of it, we have to have an integration of the x of t with e to the power minus j 2 pi ft. This e to the power minus j 2 pi ft can be broken down into a cos and sine signal, as we know that e to the power minus j omega t can be written as cos j omega t uh, plus j sine omega t. So as even the statement says that it will be splitting it into its constituent sinusoidal components. That's what we'll do over here. And we integrate it within the limits of minus infinity to plus infinity, where we have x of s as the Fourier transform of x of t, and f represents the frequency range of this signal. And e to the power minus j 2 by ft is, as I said, it is a complex exponential that allows for sinusoidal decomposition. The inverse Fourier transform enables us to reconstruct the original time domain signal from its frequency components. As we have a Fourier transform, we also have an inverse Fourier transform so that we can recover back the time domain representation of the signal to do a respective study according to the time domain specifications also. Now looking at a few properties of Fourier transform, like the linearity property, time shifting, frequency shifting property, and convolution property. So the linearity property, where we have the two signals which can have two separate amplitudes, and when you go for the Fourier transform of it, we have it as a of a into x of t plus b into y of t. We'll be having the Fourier transform as a into capital X of f plus b into capital Y of f. It just says that if you have two signals together, added together, and if you take the Fourier transform, it will just give you the same signal with its Fourier transform without changing any of its amplitudes. And even if you have the signal separately, that is, you take the Fourier transform of the x of t, a x of t signal and b y of t signal separately, and then you finally add it also, you'll be getting the same value. So that is what the linearity property states over here. And the time shifting property states that if there is any time shift in the time domain of the signal, then you'll also see a time shift in the frequency domain also. That is, if there's a time shift of t naught as we've taken over here, you'll also have a time shift of t naught in the frequency domain signal also. There will be a similar time shift and there won't be any variation in the time shift. Then frequency shifting. A shift in frequency is represented by the modulation in the time domain. And the convolution property, in convolution, the convolution in the time domain translates to multiplication in the frequency domain and vice versa. That is, from frequency to time domain, it will be convolution once again. And this property simplifies filtering and system analysis. So it helps us to easier the filtering process of the data and also to analyze the system much more efficiently. Discrete Fourier transform. We require to know about the discrete Fourier transform in this concept is because discrete Fourier transform is something that we'll be using mostly in the signal processing, and that too we are focusing mostly on the digital signal processing. So it is mainly used to gather up all the data of discrete signals and to study them. So in digital signal processing, we work with sample signals rather than continuous time signals. The discrete Fourier transform is a discrete equivalent of the Fourier transform, typically computed using the fast Fourier transform algorithm. And the equation is given by x of k, that is the discrete Fourier transform of the discrete signal x of n. So that will be like summation of n equal to 0 up to n minus capital N minus 1. And this capital N specifies the number of samples. And we'll be adding up all the x of n signals with e to the power minus j 2 pi by n kn, where x of k represents the frequency component at index k and n is the number of samples in a signal. The fast Fourier transform and efficient algorithm for computing the DFT is widely used in real-time processing due to its computational efficiency. So now let's look at some of the applications of these discrete Fourier transform in the signal processing methods. So first one is spectral analysis. The application of it is used to analyze the frequency content of the signals, crucial in audio and biomedical signal processing. One good example is that it can be helpful in identifying dominant frequencies in audio signals. Example, voice pitch, and music harmonics, or detecting abnormalities in ECG signals. The next application is filtering. As we saw that this helps us to filter in filtering the signals. That is a discrete Fourier transform, and convolution helps us in filtering of the signals. So they help in designing filters low pass and high pass and band pass by manipulating frequency components. Example is it helps to remove noises from audio recordings or isolating specific frequency bands in telecommunication. So next one is modulation and demodulation. It helps. The application is it is used in transmitting and receiving information over various media. We definitely know that signal processing is one of the methods that we use to send or receive data over a wider range. And an example is that Fourier transform is essentially used in analyzing and implementing modulation schemes in communication systems like AM and FM. Now, next going to image processing applications in image compression. Example JPEG and edge detection. Example, the Fourier transform helps in compressing images by discarding less critical frequency components, resulting in reduced storage. Now, looking at system analysis and control applications, analyzing system response and stability in the frequency domain. And the example is used in control system design to analyze frequency response, enabling engineers to design stable and responsive systems. Now, looking at time frequency analysis, this is the last application of it. For signals where frequency content changes over time, something like EEG and neuroscience, where you have the signal that constantly changes over time. And example for this could be short time Fourier transform that is used in speech processing to analyze how sound frequencies change over time. So these are all the applications of Fourier transform in signal processing. And the conclusion for this session is that it allows the signals to be studied and manipulated in the frequency domain. Its application in spectral analysis, filtering, modulation, and image processing highlights its versatility and importance across different fields. So this is all for this video. Thank you.